This video is going to show you the application of some of the characteristics of capacitors in parallel. What do you notice about the capacitor's charges? So these are not the capacitances, but the charges sitting on the capacitors themselves. Let's see if you've noticed something and kind of came up with your own rule. Let's try a little quiz. What is the charge on the unknown capacitor? Hopefully you've seen that it's 90 picocoulombs. So the sum of the charges coming into a junction has got to equal the sum of the charges leaving the junction, because it's all got to be conserved. And when it splits up into two branches on a parallel circuit, whatever one branch gets, the other one gets the remaining pieces of. So the 30 and the 90 have to add up to 120. Now just to be clear, we can have the rule look like it's not being followed when it is, and that's if you had a circuit that looked like this. So I've got 120 picocoulombs, but in the top branch now I have two capacitors. But you got to remember the reason why the charge is the same on capacitors in series. And I'm not going to go through that now, that was done previously. But it still works out that the top branch is going to be the 30 picocoulombs, the bottom is going to be 90, and they add up. That second resistor doesn't have anything to do with the total amount in the top. It looks like it does, but it doesn't if you think about how that second capacitor gets the same charge as the first. So here's a little circuit where you have to remember that the voltage stays the same for capacitors in parallel. So if this is true, then I know that the capacitance is equal to charge over voltage. So the charge on each one of these capacitors is proportional to the capacitance itself. So that's for things that are in parallel. So the bigger the capacitance, the more charge it has. Here's another way of kind of reasoning out what's going on. My duct theory. So let's say the ducts are in the river and the ducts all carry a charge. And my river is kind of like my parallel plate capacitors, where the plates are like ponds, and then I've got this wire where the water's flowing through it with ducts on it. And the ducts travel and they hit this junction and they split up, the small pond and the big pond. Small pond only holds 4 ducts with their charge on it. The big pond holds 8 ducts. And look at my capacitor circuit above. The 6 microfarads is twice as big as the 3. And if you look at my ponds, one's twice as big as the other. It's got twice the area, and so it has twice the charges. So it's a 2-to-1 ratio. Or you can look at it as one of these capacitors gets 1/3 the total charge coming in, and the other one gets 2/3 the total charge coming in. So I've got this total amount coming in, and the top one gets 1/3. In other words, part divided by the whole, 3 divided by 3 over 6, or 3 over 9, and that's going to be 1/3 the total. The bottom one is 2/3, so that's 6 microfarads divided by 3 microfarads plus 6 microfarads. 6 divided by 9, that's 2/3 the total charge. So that way we can proportion out how the charges go to the capacitors. Another question, which capacitors store the most amount of energy? The 7 or the 3? Okay, let's look at the answer. So the total energy stored is equal to 1/2 CV squared. In this example, the voltage is the same for capacitors in parallel. So the voltage isn't a factor here. So what we're saying is that the energy in a parallel circuit is directly proportional to the capacitance. In other words, the bigger the capacitance, the more energy it can store in a parallel circuit. So that means that the 7 is going to store more energy than the 3 in this circuit.